Okay, we'd better get going. See, I'm learning as well. So, yeah, apologies for the lateness. I was heading to the wrong theatre, which also isn't a good sign. But anyway, let me continue straight on with where we got to on Friday's lecture. So I kind of ran out of time introducing this concept of a potential vortex. So I just want to devote a little bit of time to go back over that. So where we were on Friday was that we'd started off with this stream function that satisfied conservation of mass. We'd introduced the potential function psi, which immediately satisfied conservation of momentum via that irrotationality condition. And then we cunningly noticed that there was a relationship between the stream function and the potential function that satisfied this Cauchy-Riemann set of equations. And that means that we can express really any flow that can be expressed in terms of a stream function and a potential function can now be expressed as this potential, this complex function W, which we call the complex potential. And I was trying to explain you or persuade you why that might be useful. And I think hopefully I was going some way to showing you that this could give us quite elegant solutions, both algebraically and when we start to try to compute or solve these flows numerically. So I guess the immediately attractive thing is that it's compact. If we can express a flow in terms of the complex potential, it means that there's a stream function and a potential function for that flow, and that means that it immediately satisfies all of those governing equations of motion. So in that sense, it's kind of reassuring. If we can express a flow in this way, then we can forget about all of those conservation equations that we started this course with. So, and then moving on from that on Friday, what we showed was that, and this is really just a cheat sheet, I guess, this slide for your revision purposes, but what we showed was that if we differentiate that complex potential with respect to Z, which is very convenient for us in almost every situation, if we differentiate that complex potential with respect to Z, we can obtain those velocity components. We obtain dw dz is equal to u minus iv, so the real part of dw dz would be equal to the horizontal component of velocity, minus the imaginary part of dw dz would be equal to the vertical component of velocity. And even better, if we just multiply dw dz by that complex exponential, if we multiply it by e to the I theta, we can obtain the radial and azimuthal components of velocity. The real part would be the radial, and minus the imaginary part would be that azimuthal component of velocity. And I hope we kind of looked at that example of just flow over a cylinder, and this was pretty simple, if you recall. Actually differentiating the complex potential for the flow around the cylinder with respect to Z was very, very straightforward algebraically, and then splitting that up into its real and imaginary components was also incredibly straightforward for getting those velocity components as well. And then there would be a few other things that we'd have to remember here just in terms of handling complex numbers, but that didn't ought to cause any of you any problems. It's just a matter of dredging complex numbers up from the recesses of your memory. How long ago did you, other than this course, where else are you using complex numbers in other courses this semester? No? Yes? Some of you are. All right, so you should be pretty fresh with this kind of stuff. It shouldn't have been too long. It certainly shouldn't have been as long for you as it has been for me. So where I got bogged down on Friday was trying to explain this kind of weird animal that's a potential vortex, okay? So, and to be precise, it's an irrotational vortex, which sounds kind of like an act of stupidity, right? How a vortex sounds like something that would be inherently rotational, since we define irrotational flow as flow where the vorticity is equal to 0. So, how can we have a vortex that's irrotational? So I thought you'd come across this potential vortex in earlier courses, but I was obviously incorrect. So I will just kind of labour it a little bit more. So a potential vortex is just a weird sleight of hand, all right? You define the velocity field associated with a rotational flow in such a way that the vorticity is exactly equal to 0. And precisely what we do is we define a potential vortex as this rotating flow. So it has circular streamlines, and we define it such that that azimuthal component of velocity u theta is inversely proportional to the radial distance from the center of that vortex. So u theta is just equal to c on r, and we define that the radial component of velocity ur is equal to 0. All right? And it's trickery. If we look at it algebraically, it's an act of trickery. So if you consider some element on moving around one of those circular tracks or circular streamlines, you can calculate the vorticity of that element. So all I've done here is convert that definition for vorticity, du dz minus dv dx. I've just converted that into cylindrical polar coordinates using those techniques that we went over in lecture 3. So I can express vorticity in cylindrical polar coordinates, and that's the equation for vorticity at the top of this slide. And what you notice is that under this definition, I'm saying ur is 0. So one of those terms disappears from that vorticity equation, and I'm saying u theta is equal to c on r. So if u theta is equal to c on r, that means that that other term in that vorticity equation, du theta dr, all I've got to do is differentiate c on r with respect to r, which is just going to equal to minus c on r squared. And hey presto, when I substitute what I've got for u theta and what I've got for du theta dr back into that equation for vorticity, you get the result that we're looking for, which is that vorticity associated with this obviously rotating flow is equal to 0. And I'll try and explain the trickery better than I did on Friday. So if you just considered, say that u theta didn't diminish with radius, so u theta was just constant, and then you've got solid body rotation, so that actually u theta, yeah, so I just had solid body rotation about the center of that point vortex. In that instance, a vortex element on one of those circular tracks, or on one of those circular streamlines, would rotate. Do you agree? So as you follow that element as it moves around that circular track, it's rotating, right? If it's solid body rotation. And which way is that element rotating as you're looking at it? Clockwise or counterclockwise? Yeah, all right. It's rotating in that counterclockwise direction. So if I had, let me just run this. Let me run this. I didn't run these on Friday, right? I didn't run a MATLAB script. Okay. So your memory's now getting better than mine. Okay, so with that solid body rotation, as that element moves around that circular streamline of that potential vortex, it's just going to rotate, okay? And I know this just looks like a crappy cartoon, but it's really I'm really calculating the rotation of that element as it moves around that circular streamline and plotting it, okay? So that solid body rotation, for the case where we have u theta inversely proportional to that radial distance, what happens, and it's a trick, it's a sleight of hand, what happens is that there's this mismatch of those azimuthal component of velocities on that inboard and that outboard face of that element, okay? And what sense is that velocity mismatch going to rotate that element in? The other way, yeah. a very bored voice saying the other way. Okay, so it's fair enough, all right? It was a silly question. I deserved that answer. So it's going to rotate it the other way. And what it is we've set up that that diminishing u theta with radial position in such a way that it perfectly unwinds that rotational element as that fluid element, sorry, that rotational component as that fluid element moves around that circular streamline. So what we end up with, let me run the case of the potential vortex. So the solid body rotation is shown by that cyan square, and the potential vortex is shown, what happens with the potential vortex is shown by that red square. And we just have this perfect balance, right, where that tendency to rotate in that counterclockwise direction is perfectly unwound by that, that mismatch in u theta, which is going to rotate it or unwind it the other way. So that element goes around that circular track just like a car on a Ferris wheel. It's completely irrotational. It maintains the same orientation. So you can have a flow that's moving on a circular streamline or a curved streamline pattern without having vorticity or with it being still irrotational. Okay, so a vortex defined in this way is irrotational, and then I've put this caveat or disclaimer, which is ish. All right, it's irrotational-ish. Why am I saying that? Where's this potential vortex not going to be irrotational? Yeah, right at the center. Okay, there's all kinds of weirdness going on right at the center. But right off the bat, you can see that u theta is going to be equal and opposite now on each sides of that element, and it is indeed that fluid element would rotate right at the center of that potential vortex. And there's other problems, right? Because we define u theta as equal to a constant divided by r, and then as r asymptotes towards 0 at the center of that vortex, and u theta is going to blow up, and it's going to become infinite as well. So there's all kinds of other nastiness going on right at the center of that potential vortex. But we've dealt with this before. There's also nastiness or singularities that are occurring at the center of sources and sinks, and we kind of knew to avoid those areas when we were analysing flows. So what I'd also, just before we move on and think about this potential vortex a little bit more, at the moment we've got this constant c in that definition for u theta. It would be useful to kind of rewrite that constant c in terms of something that something that had some physical meaning. And what we use is this concept of circulation, for which I'm using this capital symbol gamma. So if you want to read a little bit more about circulation and a more mathematical description of circulation, then you should look around page 54 in your lecture notes. And you'll also find a proof of the relationship that I'm giving you on the next slide. But for now, circulation gamma is defined as the line integral of velocity, the tangential component of velocity, around some closed loop within a flow field. So if you imagine I had a flow field with these curved streamlines that are shown here in blue, I could draw some, arbitrary closed loop through that flow field, and then circulation would just be defined as the line integral of that tangential component of velocity acting around that loop. So in this instance, if you considered some small element of that loop, and I'm going to call that element ds, what I want to consider is the integrated component of velocity that's tangential to that element around the loop. So if I define the surface normal vector to that element as n, I can then define an angle between that local velocity vector v and that surface normal n as this angle alpha. And then that definition for circulation is relatively straightforward, that I know that we'd still have to find that surface normal, and we'd have to find alpha. So in practice, it could be a little bit more tricky. But you can see that that normal component of the component of velocity that's acting tangential to that element, which is shown by this orange arrow, would just be equal to that local velocity vector v multiplied by sine alpha. And then all I have to do to calculate the circulation associated with that flow is just integrate all those tangential component of velocities around that closed loop in this flow field. So circulation is just that line integral of v sine alpha ds. And there's a relationship, I should say there's a relationship between circulation and vorticity, which I'll show in just one moment. So defining the circulation for that potential vortex is quite straightforward. If I choose a closed loop that's just equal to one of those circular streamlines, then all I've got to do is integrate that tangential component of velocity around that closed streamline. And since on that circular streamline I know that the radial component of velocity is equal to 0, I know that v is just equal to u theta, and I know that sine alpha is just equal to 1. So that v sine alpha term in that equation for circulation at the top there, remember that's just the v sine alpha is just the tangential component of velocity around that closed loop. That v sine alpha term will just become u theta. So and u theta is invariant around that loop, so the circulation is just going to equal to u theta multiplied by that line integral of ds. And that line integral of ds is going to equal what? It's going to equal the circumference of that circular streamline. So it's just going to equal 2 pi r, okay? So that circulation gamma is just equal to u theta multiplied by 2 pi r. So the only advantage here really is that we can now rewrite that azimuthal component of velocity where we did have that u theta was equal to some constant divided by the radius. I can now rewrite that azimuthal component of velocity in terms of the circulation. So it's equal to this circulation gamma divided by 2 pi r. So that constant c that we were dealing with initially just really it quantified the strength of the circulation associated with our potential vortex, effectively. So if you compare it to that previous definition of u theta equals c on r, you can see that that constant was just equal to circulation on 2 pi. So I guess all we're doing is just we're giving that potential vortex a strength or a magnitude, effectively, and that magnitude is measured by circulation. So all right, so here I guess is yeah, that statement is correct. The circulation on all streamlines about a potential vortex is going to be the same, okay? And the circulation of most closed loops around actually the circulation of any closed loop that surrounds a potential vortex will also be the same. But there's this subtlety here, okay, that I just want to talk about, and it's related to that ish that I said, that potential vortex was irrotational-ish. So circulation is actually related to vorticity via this relationship that's given here. And again, this relationship's proven on page 54 of your lecture notes in quite a complicated, I think in quite a complicated fashion. But you can very easily, if you go back to our definition of vorticity, where we considered the rotation acting on that on a square fluid element, and you just calculate the line integral of the velocity around the edge of that square element, you immediately arrive at this you immediately arrive at this definition. So circulation is effectively just equal to vorticity per unit area. Or put another way, the circulation is the line integral of the velocity around some closed loop. But that circulation is also equal to the integrated vorticity within that closed loop multiplied by the area. Okay. So if you feel the need, you can prove that expression on page around page 54 of your lecture notes. So there's a weirdness here, right? So if I've got this point at the center of my potential vortex that isn't irrotational. It does have a vorticity. It is rotational. And yet that equation says, I mean, I know that if I draw a line, if I take a closed path around that point vortex, I can define a circulation associated with that point vortex, all right? And that circulation is just going to equal to 2 pi multiplied by that constant c that we've been using. So, and it doesn't, I guess what that statement before implied is that it doesn't matter where I take that closed loop. But if you think about it, it does. If there's a circulation, then there's also a vorticity associated with that potential vortex. But that vorticity is where does that vorticity exist? You know, if I integrate the velocity around that black loop, I'm going to attain a finite value for circulation. And then that equation right at the top there tells me that if there's a finite value for circulation, there's a finite value for vorticity. And yet I was calling this an irrotational flow. But where's that vorticity coming from? It's coming from the singularity, right? It's only at the it's only at the center of that vortex. So sometimes, if those of you using textbooks or other sources, other reference sources for this course, you'll sometimes find that a potential vortex is also referred to as a point vortex because it's just it's a singularity of vorticity that exists only at a point. So if I drew some other loop, as long as that center of that point vortex was still in that loop, it would have that same value of circulation. But if I draw some other closed loop through the flow that didn't contain that center of that vortex, it would have a circulation of 0. So I'm not really going anywhere with this, I guess. It's a weird beast, all right? We're dealing with irrotational flows so that they satisfy our governing equations of motion. We've introduced this new building block flow, which is a potential vortex. It has these useful properties. It satisfies our governing equations everywhere except right at that center point of that vortex. And we've got to be a little bit careful of that fact that we've got this singularity at the center and we're violating our equations for motion, of motion. But nonetheless, it's a very, very useful building block flow for us for kind of making inroads into understanding more complicated fluid flows. So let's have a look at it and let's kind of monkey around with this potential vortex a little bit. So the first thing that we have to do is really write out an expression for the, well, actually, what I want to do is write out an expression for the complex potential for this potential vortex. But in order to be able to do that, I have to be able to write out an expression for the stream function and the potential function for this point vortex. So we have that u theta is equal to circulation divided by 2 pi r. And I've got that the radial component of velocity, ur, is equal to 0. That's the velocity field that's associated with that point vortex. If we go back to our cheat sheet, you can see that I've got these expressions that are going to help me convert from those velocities into the stream function and the potential function. And I think in this case it's a no-brainer. We're dealing with something that has circular streamlines with a defined azimuthal component of velocity, so it makes sense that we work in cylindrical polar coordinates. So what I'm going to use are those relationships between UR, U theta, and the stream function psi. So I can just substitute those relationships for, so U theta becomes minus d psi dr, and UR becomes 1 on R d psi d theta. And then it's the same MO that we followed for all of those other building block flows. I then have to integrate those equations to get an expression for that stream function psi. So d psi dr is equal to minus gamma on 2 pi r. So the stream function psi is equal to pi on 2 pi r integrated with respect to the radius. So what's that going to be equal to? If we start off just looking at that equation on the left-hand side there, what is the stream function going to be equal to if I integrate that expression? Yes, I think I heard it, right? Minus gamma, I think you might have missed a minus sign, minus gamma on 2 pi log r plus this unknown function of theta, which I'm going to call f1. And if I integrate that equation on the right-hand side, it's even easier. It's just saying that psi is equal to 0 integrated with respect to theta. So I'm going to get 0 plus some unknown function of r. So f2, that function of r, must be minus gamma on 2 pi log r. And then f1, that function of theta, must be some constant. So what we've got by comparing those two simultaneous equations is that the stream function is equal to minus gamma on 2 pi log r plus some constant of integration. So that constant of integration we're kind of free to select, but we usually choose it so that the stream function is equal to 0 at some radius b. So we make that constant. We really make that constant equal to plus gamma on 2 pi log b, so that that stream function is going to equal 0 at some given radial position b. So does that make sense? So b was just b is just it's a constant of integration, and I'm just it's a datum. It doesn't make any difference to how we calculate our flows. It's just a convention that I could establish a convention where that stream function would be equal to 0 at some radial position equal to b. So, for example, if I wanted the stream function to equal 0 when r is equal to 1, then I'd just end up with that simple form of the stream function shown at the top there, right? Because log r is equal to 0, so stream function would be 0 at r equals 1. So all I can say is that constant of integration has very little impact on us. It just defines the value of the stream function at some certain point. But the value of the stream function is meaningless. It's the difference between the stream function of adjacent streamlines that has any relevance or any meaning on the flow field. So anyway, that's the equation for the stream function associated with that potential vortex. And then to obtain an expression for the potential function, we can just make use of those Cauchy-Riemann relationships in cylindrical polar form. We've got this nice set of relationships between the stream function and the potential function. And in cylindrical polar form, they're given at the bottom of this slide. Does this make sense to everyone? So, you know, I've got two expressions on this slide for u theta. I've got u theta equals minus d psi dr, and I've got u theta equals 1 on r d phi d theta. And if I just equate those two definitions for u theta, I obtain this relationship between the stream function and the potential function that I'm highlighting at the bottom of this, at the bottom of this slide. Okay, so it looks nasty, but it's actually very straightforward. So all I've got to do is differentiate. Well, I've got to multiply my expression for the stream function by -1, then differentiate it with respect to r, and that's going to equal to 1 on r d phi d theta. And remember, I want to get an expression for phi, the potential function for this point vortex. So gamma on 2 pi log r differentiated with respect to r is going to equal 1 on r d phi d theta. Very sneaky while my back was turned, look. So there's no shame. Just leave whenever you want. It's only me who has to stay till the end. So gamma on 2 pi log r differentiated with respect to r is just gamma on 2 pi r, and that's going to be equal to 1 on r d phi d theta. So those r's on the bottom of the left-hand, right-hand side of that expression disappear, and then the potential function is just equal to the integral of gamma on 2 pi. So it's just equal to gamma on 2 pi integrated with respect to theta. And you should all be able to do that integral, okay? So phi is just equal to gamma theta on 2 pi. So now we've got expressions for the stream function, and we've got expressions for the potential function, and now I can just mash those together to get an expression for the complex potential W for this point vortex. So is everybody following what I'm doing here? Yeah, I think I'm making a meal of it. I just want the complex potential, but I can't define the complex potential without first defining the stream function and the potential function. So W is equal to phi plus I psi. And I've got definitions for phi and psi that I can substitute into that expression for W. There's a gamma on 2 pi in both of those terms, so I can take that outside of a bracket. And then I just need to deal with that bracketed term, theta minus I log r. And this is a case where kind of being slightly fresh in terms of complex numbers can help you simplify that expression in the brackets. So to make life easy for myself, what I can do is what I'm doing is taking minus I outside of that bracket, so that theta term becomes I theta, and that minus I log r term becomes log r. Does everybody see what I did there? And then, well, I guess this is the trickery, right? I want to make that first term in the bracket a logarithmic term. So if I want to express I theta as a logarithm, what do I do? This is too obvious. You know this, right? Yeah. So if I can express that as the natural logarithm of e to the I theta, okay? So I think it's obvious that we can do that. It's just remembering to do it when you reach a dead end or you get stuck in a derivation, okay? So now I've done that. It's very convenient, right? Because log r plus log e to the I theta is actually just log r e to the I theta. And what does r e to the I theta equal? Z, okay? So it's beautiful. That complex potential function for a point vortex is actually just equal to minus gamma on 2 pi log z, a very, very convenient form. And remember that to get velocity components, all I've got to do is be able to differentiate that expression for W with respect to z. And differentiating that expression with respect to z isn't going to cause anybody any problems. Okay, so I guess what we typically like to do is look at the velocity field associated with, well, not just, I mean, at the moment we've got one point vortex, but moving forward with multiple point vortices. So you know how to get the velocity, right? Now we've got the complex potential function. All I've got to do is differentiate that expression with respect to z. So dw dz is equal to u minus iv, and dw dz is going to equal to minus I gamma on 2 pi z. Okay? The differential of log z with respect to z is just 1 on z. So what I've got to do is somehow separate that expression for dw dz into a real and an imaginary components, and then I can get the horizontal and the vertical components of velocity u and v. So obviously I've got to substitute for that complex coordinate z in that equation. So I can substitute that z is equal to x plus iy. Still not really helping me, right? I want to split this into a complex and an I want to split this into a real and an imaginary component. But there's that trick that we can always remember. I can get rid of that complex number on the denominator of this fraction by just multiplying through by that complex conjugate, x minus iy. So if I multiply the top and bottom of that fraction by x minus iy, the bottom just becomes real, x squared plus y squared, and then I've got this x minus iy remaining on the top, and now even I can split that into a real and an imaginary component. So you can see that I've got this minus I gamma multiplied by minus iy, so that's going to become I squared gamma y, which is going to become minus gamma y. So that's the multiplier for my real component of dw dz. And then we've got this minus gamma x, which is gives me that imaginary component. So we've got u is this bracket, this underbrace term here, and we've got minus iv. So v is that the negative of that imaginary component of dw dz. So it's easy, right? It's easy to get an expression for w. It's easy to differentiate w with respect to z, and hence it's easy to find those components of velocity that are associated with this potential vortex. So let's just have a quick look at it in MATLAB, okay, or how you would do this, how you'd have a quick look-see at a potential vortex in MATLAB. So it's kind of the same starting point I've been using a lot. The first thing that I would do is set up a mesh of x and y coordinates. So are you using that mesh grid command at all for anything that you do with MATLAB or your assignment? No. So mesh grid, that command is just going to set up two matrices of x and y. And it's going to set me up a bunch of points in x that go from -5 to +5 in x in steps of 0.2. And then it's going to set me up a bunch of points in the y direction that also go from -5 to +5 in steps of 0.2. So this mesh grid command is going to return me two matrices, x and y, each of which is 51 by 51 points. So it's really defining a grid of coordinates from -5 to +5 in x and y direction. It's defining a grid of x and y coordinates. All right, so the z, that complex coordinate, is then just equal to x plus I times y. We know that dw dz is just equal to minus gamma divided by 2 pi z. And gamma is the strength of that potential vortex. So I'd also have to define gamma here. For the case that I'm showing, I've just said that gamma is equal to unity. It's just equal to 1. So I could either, if I wanted to look at the u and v components of velocity, I could either make use of those equations that we just derived, or I can be even lazier. I can just say that u is equal to the real part of dw dz, v is equal to minus the imaginary part of dw dz, and then we can just plot the vector field associated with this flow. Have any of you used the quiver command yet in MATLAB? No. All right. Well, it's no shame in that, because I guess it's a command that's primarily used for fluid dynamics. I haven't really explained it yet. But for a given u and v component of velocity, quiver will just plot a bunch of velocity vectors that show the local magnitude and direction of the velocity based on that u and v component, okay? And it will plot those vectors at these x and y positions. So for quiver, you just plot x, comma y, comma u, comma v. Okay? So x is equal to the real component of z, and y is equal to the imaginary component of z. So when you use that plot quiver, you can plot a vector field that's associated with that point vortex or that potential vortex. It's a little bit more complicated than I'm making out, all right, because those velocities blow up at the middle of that vortex. So I'm blanking out the middle of that vortex where all that nastiness occurs, where those velocities tend to infinity and where that flow is rotational. I'm just actually, I'm kind of excluding that region from this plot. I've set all of those velocity vectors equal to 0 in that exclusion zone or in that region. So that's what a point vortex or a potential vortex looks like. So, and then it's kind of useful, right? We can use that point vortex for all its limitations and all of the caveats and assumptions that we've made in this course. We can now use that point vortex to start kind of trying to understand what happens where we've got vortices in flows and where we've got vortices interacting with other vortices or interacting with solid bodies in a flow field. So let me talk just for a second about vortex-induced motion. So that vortex on its own if that vortex is in isolation, and I ran this simulation as a function of time, it's just going to remain absolutely stationary. Okay, that vortex or that flow is in equilibrium. It's not mutually inducing itself to move in any direction. Okay, I guess this is kind of back to front. I should show the other case really before you believe me that occurs. So a vortex on its own would just remain stationary. It's not going to go anywhere, okay? But that isn't true when we've got multiple vortices in proximity to each other, okay? So a pair of vortices are going to induce motion in each other. And it's pretty easy to explain. I think it's pretty easy to understand why. So this is a pair of vortices, a pair of counter-rotating vortices, and they're turning in a sense so that the flow between them is moving downwards. Okay, so the flow on the flow on the left is rotating in a clockwise direction, and the vortex on the right is rotating in a counterclockwise direction. So let me start off by just considering this vortex on the left-hand side. All right, it's rotating in that clockwise direction. And if you imagine that vortex in isolation, it would induce a velocity at the midpoint or the center of that other vortex. Do you agree? It's got a velocity field associated with it, right? It will induce a velocity at the center of that other vortex, that one on the right-hand side. And which direction is that induced velocity going to be acting in? Down, right? It's going to induce a downwards velocity at the center of that other vortex. And likewise, that vortex on the right-hand side is also going to induce a velocity at the center of that left-hand side vortex. And again, it's going to induce a velocity that's downwards at the center of that vortex. Can everybody see that? So, I mean, if you just kind of imagine one of those vortices wasn't there and just imagine the pattern associated with the other vortex, just consider, that vortex is making everything orbit around it, okay? And you can consider that direction of that orbit at the center of that other vortex, okay? So they each induce each other to move downwards. So in this case, those point vortices are going to move as a function of time. There's a induced velocity at the center of each vortex, and you can treat those point vortices exactly as you've treated those particles that you've been advecting around for your assignment using Eulerian or RK4 schemes. Does that make sense? There's a velocity at the center of each of those vortices, and if I now look at some time step in the future, dt in the future, each of those point vortices is going to have moved by a distance which is equal to that induced velocity at the center of that vortex multiplied by that time step dt. Remember, that vortex is really just a singularity or a point in space where that vorticity exists. So if I were to run this in time, both of those vortices mutually induce each other to move downwards, all right? And if I ran them in time, they'd just move down towards the x-axis, all right? So remember, now imagine that the x-axis was a solid boundary, okay? So if I wanted the x-axis to be a solid wall, what does that mean would be taking place below the x-axis? Sorry? The image flow features would be occurring, right? Like in that smoker's problem. So you'd have vortices below the wall that were turning in the opposite sense. So can you see what would happen when those vortices reached that solid boundary? Which way would they go? Outwards. They'd go outwards, right? They'd go downwards and they'd reach that wall, and then they'd start migrating outwards along that solid wall because of those image flow features that exist. So let me just play this movie. All right, so an aircraft has a wing that generates lift, okay? And for a large aircraft, it has to generate a lot of lift. It has to generate a lift that's equal to the mass of that aircraft, all right? And as we'll see going forward in this week and next week's lectures, in order to generate a lift, that aerofoil of that aircraft has to have a circulation around it, a large circulation. And where that circulation reaches the end of the wings, the wingtips, that circulation is shed or trails from the tips of the wings of that aircraft as these trailing vortices. And those trailing vortices turn in that same sense as that counter-rotating vortex pattern that we just looked at. So if you look, what's happened is they've got these two plumes of smoke. They're going to fly an aircraft between those plumes of smoke, and you're going to see those wingtip vortices coming off the tips of the wings. And then what you should see, those vortices turn in that sense that I showed with common flow down between them. And what you should see is that those vortices migrate off downwards. Okay? So there's those wingtip vortices, and then they mutually induce each other to move downwards. And you don't really see it here, but once they reach the wall, they'd start to migrate outwards along that wall. So what about this case, all right? Now, this is a trailing vortex off the back of the wingtip off the rear wing of a racing car. So which way are these ones going to turn? So this is not generating lift, right? It's generating negative lift. It's not trying to make that racing car take off. It's trying to stick it down onto the road so it's got maximum traction. So those counter-rotating wingtip vortices in this case are rotating with common flow up. So as they come off the back of the wing of that F1 car, they're going to migrate away from the wall and away from each other, okay? Although you can see them turning in the other sense in this video, so it's spinning in the other direction, but you can't really, I guess you can't clearly see that vortex migration. I should. Never use YouTube in classes, all right? So you see they've flown this plane a long way away from this mast that has this smoke coming from it. It's generated this pair of counter-rotating vortices off of the wings of that aircraft, and it was pretty high up, right? And then those vortices have migrated downwards onto the field, okay? And then they're migrating outwards because of those image vortices towards this mast. And if you watch this movie for long enough, you'll see that those trailing vortices from that aircraft are remarkably persistent. Eventually, they reach this mast, propagating outwards across that field, and you see that this smoke gets rolled up, or those smoke streams gets rolled up into the cores of those vortices, okay? So we can start to use this potential vortex model to predict where those Fortunately, there was no music. But anyway, we can start to use this model for potential vortex to predict how these things are going to behave in real life. Yep.
So when we are calculating Fy, we're using P upper and P lower, so which is like
Yes.
node 1 and node 30, node 2 and node 29.
Yep.
But what about like P front and P back?
Well, that's when you're calculating drag.
X.
Right. Yeah, so that's for calculating the drag. So I think the thing that you've got to go careful with both of those is that the taps that are on the front or the back of the aerofoil change with angle of attack. Subtly. Do you know what I mean?
Yeah.
If that aerofoil is at 90 degrees, everything on the bottom is now the front, and everything on the top is now the back. So that's one of two ways you can do it, right? You can either consider f of x with this front and back separately, or you can just do that circular integration straight off the bat to get an expression for They don't have any of these.
No, they don't. Okay. I mean, of course, I could look up other literature.
You know, the best, I think these references are out of date. I would say the best approach for the laboratory is one of these.
Yeah, fundamentals.
I think the fundamentals of aerodynamics are what you do in the laboratory. But they're very nice experts, I do have to say. I'm surprised that plate isn't available in the...
Yeah, none of them are. Yeah.
Are they like all booked out, or like
They just don't have